Good day, students. Welcome to math.serve.com, and this clip we're going to be going over how to find inverses algebraically and graphically. Okay, so the instructions for the example we're going to be doing today is to find the inverse of the given function algebraically and then verify the accuracy of your results graphically with justification. So let's say for problem number 1, we have the function f of x equals 2x plus 4. Okay, the first part involves finding the inverse algebraically. So let's find f inverse of x. That's the notation for the inverse algebraically. Okay. All right, so to accomplish this, let's rewrite the function. We have f of x equals 2x plus 4. Now, what we're going to do first is we're going to carry out the switch. Okay. What do I mean by the switch? For the switch, the output becomes the input, and the input becomes the inverse of the output. Okay? So we're going to replace f of x, the output, with the input, x. And then 2, instead of x, we'll replace the input with the inverse of the output function, f to the negative 1 of x plus 4. Okay, so this is the switch step. Now what we're going to do next is we're going to solve. We're going to solve for f inverse of x, which is the inverse of f. To solve for f inverse of x, we're going to subtract 4 from both sides and then divide by 2. That will result in f inverse of x being isolated. Let's go ahead and do that. So we'll subtract 4 from both sides. That yields x minus 4 equals 2 times the inverse of f of x. Okay, now final step is to just divide both sides by 2. Divide by 2, divide by 2. And we have, we can also switch this around. We have f inverse of x, this 2 2's divide. And we can write this as x over 2 minus 4 over 2. Okay, x minus 4 over 2 is the same thing as both terms, individual terms being divided by 2. Okay, now why did I break them apart? We're going to be graphing a linear function, and it's easy for us to determine the slope on the y-intercept when the variable and constant terms of the linear function are written separately. Okay, so let me simplify it a little bit further so you can understand where I'm going. So we have f inverse of x equals, now the multiplicative identity is 1, so we have a 1 up here. So we can write x over 2 as 1 over 2x. X over 2 is the same thing as 1 over 2x, okay? 4 divided by 2 is just 2. So this is the inverse function that we are supposed to find, the inverse of f of x. Okay, so is our answer correct? The question asks us to verify the accuracy of our results by using the graphical approach. So what we're going to do is we're going to go ahead and graph the function and its inverse and see if we can verify that these two functions are in fact inverses of one another. Okay, so let's color the inverse function blue. So f of x equals 2x plus 4. Now how do you graph a linear function? Recall the formula y equals mx plus b. That's the slope-intercept form of the equation of a line. If you have a linear equation written in this form, the coefficient of x, which is m, is your slope. So m, or the rate of change, is 2 over 1. Now, where do you start graphing your rise over run on? Because we're going to be rising 2 and running 1. We're going to start from the y-intercept b. That's your beginning. Okay, b is a constant term. In this case, it is 4. All right, let's go ahead and graph that. So I'm going to graph it down here. So let's set up our coordinate system. My y-axis, my x-axis. Okay, so we're graphing, what we're graphing is f of x. So we start with the y-intercept. Okay, that's the beginning. That's always what you want to graph first. So the y-intercept in this problem is positive 4. So let's graph that 1, 2, 3, 4. There goes your y-intercept. Slope, you rise 2, 1, 2, and you run 1. That's another point on the line. Okay? And then you want to graph more points, you can rise 2 again and run 1. Just for accuracy purposes. So there goes our line. Let's go ahead and draw it. We're going to make it blue. So the line that goes through these points is the graph of f inverse. So let me make it look good right here. So that's f inverse for you. Okay, so next thing we're going to graph is the graph. We're going to plot the graph of f inverse. Okay, this is f, and then let's graph f inverse. Now, f inverse, we found it earlier. It's right here. F inverse of x is 1/2 x minus 2. So this is also in the slope-intercept form of the equation of the line, y equals mx plus b. So we can easily determine what m and b are here. All right, so for the inverse function, the slope m is 1/2, which means we're going to rise 1 and run 2. The y-intercept, where you're going to begin your rise and run from, is -2. All right, so let's go ahead and grab that. We have -2. It's down here. 1, 2. That's -2, and then we're going to rise 1 and run 1, 2. Okay. Let's graph another point. Rise 1, run 1, 2. All right, so the line that goes through these 3 points is the graph of the inverse. Okay, so let's go ahead and draw that line. Let's make it red. Okay, so graph it through the points right there. Okay, so there goes the graph of the inverse. Let's go ahead and label our functions. So this one down here, this is the inverse, f inverse of x, which is 1/2 x minus 2. And then the blue function is the function f of x equals 2x plus 4. All right, now if we draw the line y equals x, that is critical in helping us determine if our graphical representation of the function inverse is in fact correct. So what we're going to do is graph the line y equals x. So let's go ahead and do that. So the line y equals x has a slope of 1, this is y equals x plus 0, and a y-intercept of 0. All right, so start from 0, rise 1, run 1, rise 1, run 1, rise 1, run 1. So that diagonal line that divides our axis into 2 congruent halves down the diagonal, that's the line y equals x, okay? So let's go ahead and draw that line, okay? All right, now what do you notice just by observing the appearance of this graph? What you see is that these two lines are symmetric about the line y equals x. Well, what does that mean? That means that our result is actually correct. Okay, whenever you have them set up like this, they are symmetric about the line y equals x. That automatically means that our result is correct. Okay, so let's go ahead and write down the justification just to tie everything together to help us see why we can conclude that our result is correct from the graph and also from the numbers we'll be using in a minute. So justification of inverses. So how do we know that our answer is correct? We're going to be justifying graphically and numerically. So graphically, how do we know that the two functions are inverses of one another? So graphically, you can state that the graphs of f of x equals 2x plus 4 and f inverse of x, which is equal to 1/2 x minus 2, are inverses. Why? Because they are symmetric. They're symmetric about the line y equals x. Okay, so symmetry along the line y equals x of two functions indicates that those two functions are inverses of one another. Okay, now let's take a look at the numerical perspective. How can we use numbers to show that, to justify that two functions are inverses of one another? Well, we can just pick 2 points, that will suffice. If you take a look at this point is a reflection of that point. What are the coordinates of this point? This point has coordinates of 0, -2. And that point right there has coordinates of -2, 0 for this point right here. Okay? Now, what do you notice with these two coordinates? They are interchanged. They've been switched, right? So if you switch 0, -2, you end up at a point that's a reflection along y equals x on the other function. So that's an indication that these two lines are inverses of one another. Okay, let's just put in another point just to reinforce our claim. So if you take a look at this point right here, it's reflected to that point. The coordinates of this point, 1, 2, 3, 4. This point has coordinates 4, 0. Okay, when you reflect it along this line, you're going to end up right here, and the coordinates are 0, 4. So that clearly shows numerically that these two functions are inverses of one another, because when you switch the coordinates of one, you end up with the mirror coordinate on the other along the line y equals x. Okay, so let's go ahead and write that down. The functions are inverses because of what? Because the coordinates from the coordinates from f of x. Let's just put in some examples, e.g. 0, 0, -2, and 4, 0. The coordinates from f, so that one, and 4, 0. Okay, so the coordinates from f of x, for example, 0, -2, and 4, 0, are switched to get the coordinates of f inverse of x, which are -2, 0, and 0, 4. So this pattern continues. Whenever you switch the coordinates pairs of this function, you always end up with a coordinate pair on the other function, positioned in such a way that it's a reflection along the line y equals x. So this switching pattern right here is a numerical indication that these two functions that we have graphed are in fact inverses of one another. Thank you so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your study of Algebra 2 honors, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments on what we just covered, just post your questions in the comment section below, and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.